We're going to finish up thinking about the Poincare Lemma, this fact that closed and exact are the same thing on Rn. And I wanted to go back and fulfill a promise, an implicit promise, to understand these operations C and Z better. And this was intended, I wrote up this little problem intending this to be pretty easy, but then when I did it with my students, I realized that there's some subtleties. And in fact, one big thing that I sort of swept under the rug already that's very worth going back to. So the claim is that the operations C and Z are just the pullback operation through very simple maps in disguise. And so we actually want to just go back and review a little bit about the pullback real quick. So remember, if I have some map, let's say T, from maybe Rn to Rm, and I have a form over here, and I'll just illustrate that by maybe some squiggles, kind of the stacky picture, and let's say that's alpha. Then there's a notion of the pullback, and often we don't even use the parentheses. T star alpha. So this is a form on Rn, on the domain of T. And so we've pulled that back and created some new form, T star alpha, that lives on this new space. And that idea is pretty sophisticated, but it's really crucial. It was really crucial for our proof of Stokes theorem, things like that. Let me remind you some of the properties. The key properties were that T star of a function is just f composed with t. That's the root of everything. So on zero forms, it's just composed with t. So if f is a function to r, then it's very natural to create f composed with t, which is a function from this space to r. And then the other things that I basically sort of asserted this as kind of a half definition, that T star of a wedge product was the wedge of the T stars, and that T star d alpha is d T star alpha, that it commutes with wedge and d. And that's called naturality of the wedge product and of d. And depending on how you do this, you can sort of almost make those true by definition, almost, or you have to prove them. And I just kind of asserted them. Well, here's a situation that we often find ourselves in, where we have two mappings that can be composed. Let's say S and then T. And I've got a form alpha over here. Now again, I'm drawing it like with the things fitting together, but maybe they don't fit together. Maybe it's not a closed form. Well, I should be able to pull that back to here. That would be T star alpha. And then I could pull that back, and that would be S star of T star alpha. Or, without the parentheses, just S star T star alpha. So I'm going to get something here, and then I'm going to get something here. And that's a very common situation that we actually find ourselves in with forms and maps. But there's one other thing I could do. If I have a point here, I can take it through S and then take it through T, or I could just do the composition and do the shortcut. There's a map T composed with S here. And what if I took alpha and in one fell swoop use the composed map to produce something? Is it going to be the same thing? So in other words, is this equal to take the composition T composed with S and pull it back? Pull alpha back through that composition. Okay. Well, notice one thing. If it's going to work, it has to work in this way where the order of the S and T gets switched. Because alpha can only be pulled back through by T star, and then T star alpha can be pulled back by S star. Whereas when I compose the maps, the order is different. It's S and then T. And so this is the question. And the answer is yes. And this is a very, very nice consistency property of mappings. And what it's called, it goes by a name. I'll prove it in a second. It's called Functoriality. I don't think I'll say much more about functors, even though they're one of my favorite things. And the fact that the order gets switched, you refer to it as saying the functoriality is contravariant. So contravariant functoriality. Look up functor on Wikipedia, functors and categories, if you want to know more of the general theory of that. Okay. So how would we show this? Well, remember the idea. Every form is a sum of things of the form f d, x1 wedged, or j1 dx jp or whatever. It's a sum of those guys. Well, something I even forgot to mention about the pullback is it's linear, so it definitely distributes through the sums. So if it works on one of these building blocks, if those the two sides of the equation that I just erased, unfortunately, are equal for these building blocks, then they're good. Well, but we know that the star commutes through all the wedge products, including this implicit wedge product here. So if the t stars, let me write it up again. We want to know if s star t star alpha is equal to t composed with s star alpha. So if these are equal on the building blocks, the function and the one forms, then by the naturality of the wedge product, it'll be good. But let's see, t star on a d, that's just determined by d of a t star, so as long as it's good on all these functions, it'll be good. So these guys are going to be equal if and only if they're equal on functions. Well, on functions, that's a parenthesis, on functions, this is really easy. S star t star of f, well, what is t star of f? That's f composed with t. Here we're in the situation where we have, as I'm recreating the entire picture that I had before. Here we have s, and then t, and then f as a map to r. Okay, so this, we took f, and then we pulled it back to be a map here, f composed with t, and then we pull it back through s, that's f composed with t, composed with s. Okay, that's the left-hand side of this guy. What about the right-hand side? Let's see if I can squeeze it in up here. That's f composed with t composed with s, by definition, if this is an f. Okay, are these equal? Yes, you bet. That's just associativity of composition of functions. It just says that if I take a point here, and I go through this, then this, then this, it doesn't matter how I group it. It doesn't matter if I think I'm doing these two as a group and then taking a break and then doing the last one, or I do this one, and then I do these two as sort of in one fell swoop. Well, they're the same thing. Very, very, very crucial thing. Again, if you look up categories and functors on Wikipedia, you'll see that associativity of composition is one of the most fundamental things in the whole universe. And that's what shows that this works for functions, and then the naturality of the wedges and the d's and the sums mean that it works for everything. So this is a very, very handy formal property of pullbacks, and we're going to apply that in just a second. But first, we're going to go back to the context we're in, and we're going to do part A here. Show that if we define the map S in a very simple way, then this operation on form Z is nothing but the pullback by S. Okay, so what is the picture here? The picture is, I've got, let's do R2 to R3 as an explicit example. R2, we're going to embed that R2 as the XY plane, or the X1, X2 plane. So this is the plane where X3 equals 0, and S is just the function that takes a point XY and creates the corresponding point x, y, 0. Okay, it's a very stupid map. It doesn't do anything interesting, but that's okay because Z isn't a very interesting operation on forms either. So if this seems all kind of tautological, it's supposed to be, but it's good practice with the pullback terminology and stuff like that. Okay, so that says, as I wrote it down here, in general, S of all the x1 through xn is just add a 0 to put it into Rn plus 1 in terms of, and it'll be the set, the image will be the set where the xn plus 1 is equal to 0. Okay. Now, in order to get this to work, there's a subtle issue here. Here, these x1 and xn, I'm using those as variables, as just sort of hypothetical inputs to a map. But very often, we've been using x1 through xn as functions, coordinate functions on a space. Okay, so I think I want to be a little bit more careful about that to avoid confusion. And so what I want to really do is I want to have, this is going to be Rn. Here's little the map little s. here's Rn plus 1. This is more complexity notation than most people usually do, because usually people abuse this notation. Let's say the coordinates here are x1 through xn. And here the coordinates, so x1, of 3, 7, 5, it's the function that puts the 3 out. So this is a function here. Here, I'm actually going to use different letters so that it's clear when we go back and forth which one is which. Let's say the functions here are y1 through yn plus 1. And so like y3 of 5, 7, 9, 11 is 9. Okay. And then in order to not confuse variables with functions, I'm going to use maybe different letters for variables. So if I pick n numbers, a1 through an, let's say those are going to be, I just recreate those and I put a 0. Okay. So bear with me about the need for these letters. I'm not even 100% sure myself that we really need these, but it'll clarify some issues that sometimes really are confusing. Okay, so that's the definition of this, and we're using x's for Rn and y's for Rn plus 1. And I don't really have enough room to keep that stuff. Okay. And so now what I want to do is I want to calculate S star on some function dx j1. Now this guy's, I've decided that on, on Rn plus 1, so S star is going to take a form on the big space where I'm using y's as my coordinate variables, and it's going to pull it back to the smaller space Rn. And so this is going to be a building block function on Rn plus 1, or building block P form on Rn plus 1. And I want to figure out what S star does to it. Okay. Well, S star operates on all the pieces individually. It operates on functions by composing it with little s. Okay. And I'm just going to bring it back in here. So this is going to be y j1 composed with s, wedge up to d of y jp composed with s. Okay. Now there's going to be two cases here. If jp, that last one, that biggest one, if this is equal to n plus 1, then what is yn plus 1 composed with s? Well, yn plus 1 of s of some numbers a1 through an, that's going to be the n plus first coordinate of this thing that ends with a 0. And that's going to be 0. Well, okay, so that's the 0 function, and d of the 0 function is certainly 0, and so this whole thing is going to die. Okay, so this is going to equal 0 if jp is equal to 0, is equal to n plus 1, sorry. And that's exactly what we were doing. Remember, one of the things that the Z-map did is it killed anything that involved I was calling it dxn plus 1. Okay, and we'll see why I need the y, or I wanted to do the y's and x's in just a second. Okay, so let's assume then that that's not equal to n plus 1. It's n or less. Then what have I got here? F composed with s. Well, when I've got function composition, I need to be a little more explicit. Let's see, S star of all this stuff, let's evaluate that at some particular location. And I'm using a's as locations, as variables, not functions. So I pick some particular location in Rn. I look at this pulled back form, and I want to say, what is it at that location? Okay, so this is going to be F composed with S at those a's. Okay, well, that's just F of a1 through an with a 0 at the end. That's exactly what I was doing with z. It was sticking 0 into the n plus 1 slot. And then times d of, and this is where the y's and the x's pay off. Let's say this is just j1 is equal 1, for example. The first coordinate function composed with s. Well, y1 of s of is y1 of all this stuff. Well, the only thing that's different is the 0 at the end, but I'm not evaluating that function, and that's just a1. Well, that's what I would get if I just took x1 and applied it to the a's in the first place. And in general, if it's the j1th y, this is just going to be dx. And similarly, this is going to be dx jp. Now, most people would just use the same letters, xj1 here and xj1 here, but there's a subtle difference. This was the j1th coordinate function on Rn+1. This is the corresponding coordinate function on Rn. They're really on different spaces. And so it's nice to be able to say explicitly, this is the relationship between them, that the xj1 is just yj1 composed with s. It's a little too formal for most people. I hope it's not too formal for you, but I wanted to, I know when I explained it to my students, I wasn't using this kind of terminology, and it seemed like I was waving my hands. Okay. Now, this is exactly what the z operation was doing for us. It was killing the, any dxn plus 1, and then it was just putting a 0 in here and leaving the dx's alone otherwise. Okay. So that's exactly equal to z alpha. Okay. So what about, so the point is, even though the first few times you do these calculations, they seem a little bit bizarre, partly because they're so tautological with the y's and x's meaning different things subtly but being basically the same. But the point is that whenever you've got two spaces, our original goal in this inductive proof was to take stuff on information on Rn+1 and relate it to Rn. This is an incredibly natural way to do that, is considering this map. And then once you remember that pullbacks move forms around, this is exactly what you want to do. And I'm just pointing out that that's what we were doing all along with this proof with the z. Okay. Now pi star, we have Rn+1 here, and pi just squishes it down. Whoops. Pi just squishes it down to the smaller space. So I'm drawing R3 and R2 as an example, but it just squishes it down. It just just forgets the last coordinate. Okay, so that's that projection. And so a form on here, pi star, will do exactly the kind of thing we're interested in, of reinflating something in n dimensions to produce something somewhat simple, but still living in n+1 dimensions. Okay, so now what does pi star do? Pi star of f d, now this one, we start out with the x variables, because remember these were the x's and these were the y's. Okay, so pi upper star. Okay, now I do want to be able to talk about a specific point of evaluation, and that's going to be in n+1 variables. Okay, so that's f composed with pi evaluated at all that point. Okay, times d of xj1 composed with pi, wedge all the way up to d of xjp composed with pi. Okay, so this is just f of pi of this stuff. Remember, pi just kills that guy. And so that's f of a1 through an. That's exactly what we had for the formula for the C operator, the stretching operator. And then the key thing, the remaining key thing, is that here's another relationship, that if I take x, let's say x1 of pi of all the variables up through n+1, well, this just deletes this guy, but then x1, the x first coordinate, just gives me a1. Well, that's just exactly y1 of what we started with. So xj1 composed with pi is just yj1, and similarly xjp composed with pi is yjp. So pi and s are such natural, sort of stupid symbol-minded maps that they convert x's to y's or y's to x's depending on which way you're going. And this is exactly what we did to define C, although we're using this letter switch now. We take something that's defined in Rn, we use exactly the same function, we purposely don't put any dependence in the last coordinate, and then we just, if we insist on having a distinction, we just change the dx's to the corresponding dy's to remember that we're in Rn+1. But we didn't really do that before, and it didn't hurt us, but we weren't trying to be so finicky careful about the fact that we're really relating different spaces. But now we are. Okay, so let's get a few consequences of all of the stuff I've been saying. We now know that z is just s star in disguise, c is pi star in disguise. Let's just look at a very, very simple consequence of functoriality. What is the map pi composed with s? Let me do it over here just for a change. Pi of S of, and I'll use the A's for the variable names, again, being careful about that. Okay, so that starts with n variables. S inserts it into n plus 1 dimensions, and then pi projects it back down. You can probably guess what's going to happen. That's pi of a1 through an, and then 0. But guess what? Pi just forgets the last coordinate. It didn't even matter that it was 0. Whatever it would have been, it's going to go back to an. Okay. So in other words, the map pi composed with S is the identity map on Rn. Okay. So the reason I asked that is that in the proof of the Poincare Lemma, it was crucial that we used this operator CZ alpha. We took alpha, we restricted it to the 0 set of the last variable. In other words, we pulled it back by S. Then we pulled it back by pi to reinflate it. So that's pi star S star alpha. Okay. So that's interesting. That's exactly the kind of thing that appears in Functoriality. Well, first of all, let's ask ourselves, what about S star pi star? Why not do this? Why not do ZC alpha? What would that do? Well, that's where Functoriality comes in. S star pi star alpha. By Functoriality, that's just pi composed with S upper star alpha. And we just figured out that pi composed with S is the identity map. Whoa, that's not what I wanted. We take the identity map, we upper star that guy, alpha. Now, this is another very trivial part of Functoriality that I didn't even mention before. Pulling back by the identity map, it should be pretty clear, that doesn't do anything. That's the identity on forms, and we just get where we started. So S star pi star alpha wouldn't have been a very smart thing to create. It would have been uninteresting. Now, this one, pi star S star alpha, that is S composed with pi upper star of alpha. Well, what does S composed with pi do? I probably should have asked that up here. We'll make a new part here. Let's just try that real quick, and then we'll be done with this video. S composed with pi, well, we have to change this around a little bit. This is a sub n plus 1, and that's S of, just forget the n plus 1, and I'll make it a little wider, and that's just a1 through an to 0. What that does is it takes something in n plus 1 dimensions, squishes it down, and then just puts it back in with the 0 coordinate. This is really the projection onto the 0 set. So this should look a heck of a lot like just plain, well, it's kind of like pi, it's kind of like S, but it's a combination. It's the thing that stays entirely in Rn plus 1, but sets the last coordinate to 0. The reason we broke it out, we could have talked about this as kind of one operation in one fell swoop. The reason that we broke it out into two pieces, this is coming from the book by Botten 2, is that S star alpha is completely living in n dimensions. It's more clear that that's in Rn, and that's where we're using our inductive hypothesis. From this perspective, it's living in an n-dimensional subspace of Rn plus 1. It was a little clearer, it's a little more elegant in the proof if first you consider S star alpha, which was Z alpha, and say, hey, that's in Rn. I've never heard of Rn plus 1. I can use the inductive hypothesis, and then you reinflate it with pi star. But all in all, really, the effect is you use this projection map, which takes all n plus 1 coordinates and just sets the last one to 0, and pull alpha back by that map. So that's some interesting playing around with the very basic Functoriality and pullbacks with maps. Okay, just to finish it up, not to make this too long, but to finish this one up, I wanted to just cherry pick a really easy result. What we've shown so far, remember the whole point of this whole particular handout that I've been going through in the last few videos is the Poincare Lemma that says that any closed P-form on Rn is exact. And we did it inductively. Well, we never really used that it was Rn. When we went from Rn to Rn plus 1, we never used anything particularly special about Rn, just the inductive assumption that in n dimensions, every closed form was exact. And then we boosted it up to r, or just to rn plus 1, rather. Now, it was very crucial. Let's see if I can show you this. It was very crucial that we were able to do this operation, this k operation, integrating from 0 to xn plus 1 in this variable. That meant that for any x1 through xn, we've got to be able to connect in our set x1 through xn comma 0 to xn through xn, x1 through xn comma xn plus 1. So it was really crucial that we weren't doing anything really wacky in this last variable, and we didn't have any gaps or holes in the last variable. But nowhere in the proof did we actually use anything particularly special about the subset of Rn that we were using. So here's what we can actually prove. Suppose somebody has done the work to show that some open subset of Rn has this property that every closed p-form on U is exact. Then the proof goes through verbatim to show the same is true for p-forms on U cross R. Let's just say R for now. But you know what? Then we can do it again. U cross R2, U cross R3, and in fact, U cross RK for any k, and just inductively. So that gives us a little more flexibility. There's a fair number of open sets that we actually know this property already is true for, say in R1, R2, and R3. And then it shows that if I just take that and I cross that with some other extra variables, and there's nothing weird in the other variables, no interesting topology in the other variables, then I'm going to get this for those spaces as well. Now, the story goes on. There's a lot more that can be said about this. There's a lot more spaces you can prove this for. But this is a good time to stop this video.